All right, so here's the 3 ways. There are 3 ways that you can do this sigma bond. Remember, we're talking about sigma, so don't get all confused. We're talking about sigmas, which are the single bonds. Sigma bonds, sigma bonds. So notice they all have something in common. So, and I know this is confusing. That circle is not the electron. That circle is the nucleus. So I'm going to add in, so here's a nucleus. Here's an electron, and here's an electron. So now you can see that the electron regions are overlapping. So this would be like an H and an H. That's their little bond, and those electrons are moving back and forth. They're just moving all over the place in that whole region. Trying to get to grab it so I can move it. It's not letting me do it. But just imagine they're like, he's all over here, and he's all over here. They're all over the place. Now you can also do a end-on-end overlap if you have something like H. Notice that looks the same, so here's his electron. And then if we have Cl, now if you remember, Cl looks like this at the end. He also had an S also, but we're not talking about his S. His S is all filled up. So here, look. He's got just one. Notice, see, he's got an extra space. So he's got just one in that orbital. And so they're both flying all over the place because they're close enough that they can bond and be shared. And then the last example of a sigma bond, remember I'm doing that chlorine example again. So this is the very last p orbital. The other p orbitals aren't doing this. It's the very last p orbital. And you'll notice, blah, they're running all over, and this one's running all over the same place. So that shows you what those look like, and all 3 of those, again, are considered sigma bonds. They would all be drawn with just a single bond between them. Yay! And here's the Newton stuff, some Newton stuff right there. And I'm going to finish this video right here with a little thought, and I have more that I can say on this, but just a little thought. And this is the whole reason why we do hybridization. Then I'll do a next one I'm trying not to do these too long. So what we do know is we know that BeH2, BH3, and CH4 form compounds and that they have identical bonds. So I'm going to do Be. So we know for sure that this happens. We also know for sure that this happens. And we know for sure that this happens. Oops, sorry, that's an H, that's behind the screen, that's coming out from the screen. We know that happens. All right. So there's a problem with what was just going on, because what these guys are doing looks different than what was going on up in that section above here. So Be looks like this. Here's the guy in the middle. And his, if we do like his little configuration, so his 1s, they aren't involved in the bonding, but here's his 2s. So notice something. His 2s is full. If you're full, you can't overlap. Like you're full. Like look up here. Up here in this other section where we had these guys. The only ones that did the bonding were the ones that had a space. Then they can bond. Look, he's full. He can't bond. He doesn't have any room to bond. And yet science says, well, we know that this compound exists and that it does form a bond. So that's the first kind of a situation. So what's the problem with him making 2 identical bonds? Well, and that was supposed to be, sorry, BeH2. H2. Yeah, so the problem is that the sigma, or that the S orbital on the Be is full. There's not room for it to be like shared. Like he can't take it. It's not like you can take hydrogens and make like a group of 3 or something. You can't do that. All right, so that's the first issue. And then the other 2 represent another issue. So, and they also have some of the similar issue too. So with boron, he's got his 1s, that's awesome. That doesn't do anything. Then we have our 2s, and then we have our 2p. There's 1 there, right? We've got the other ones that are open. So first of all, we have 3 bonds. So what this means is that boron needs a dot apiece in each of them. But what we're seeing is, look, both of them are stuck here. And then there's 1 that's free. So you could say, okay, well, at least I've got 1 that I could bond and do things with. That's true. You do have 1. That other set is all stuck. You can't do any bonding with it as the way it looks right then. Here's the other problem, is that, we do know that there are 3 of these. And we also know that all the bonds are identical. So it's not like you can say like one is a 2p overlapping with an s and then like these two are something else weird. There's something that's going on to make these all look alike. And then the last case, again, carbons, 1s, 2s, 2p. So, hey, he's got 2, so, you know, he could help with that bond and that bond. But again, we have a problem. So this is the problem that we're faced with. It all worked fine up here because they all had a space. They all had one electron spot open that they could do the bond with and have it be a straight sigma bond, and it was fine. And these guys, they don't have the openings. We know the bonds are supposed to be the same, but the ones that do have the opening don't have enough to make the rest of the bonds. That's why everyone got to thinking about it and decided to think of things as hybrid atomic orbitals. And last note is that hybrid orbitals only affect the middle atom. So he's the one that's changing. The other guys, nope. Be's the one with the problem. Be's the one that's got to change. Same with boron, same with carbon. It's only the middle atom